Okay, section 11.11, modeling with differential equations. So here we are going to return to some of the problems that you set up in the rates of change section of differentiation chapter earlier on in the year. So let's start with example 27. The rate of increase of a population P of microorganisms at time t in hours is given by dp dt is equal to 3p. Initially, the population was of size 8. So here p is equal to 8 at t equals 0. That's what initially means. So we have to find a model for p in the form p equals a times e to the power of 3t, stating the value of a. So over here, what we need to do is simply solve this differential equation by separating the variables. So p acts as y and t acts as x. So p and dp need to go onto the left-hand side. So 1 over p dp, we'll leave 3 on that side and make dt join 3 on that side. Let's put the integral symbol. And here you could see that this is 1 over p dp, that goes to ln p. And then p's population is positive value, don't need to put modulus symbol down here. So we've got 3t plus c. Let's give it an e, so it's e to the power of ln p, that will give me p, and e to the power of 3t plus c. So let's find what c is, and that is going to be found by using p is equal to 8 at time 0. So 8 is going to give me e to the power of 3 times 0 plus times c. So c is going to be ln 8. So over here, if you can see, c is ln 8. Before I apply the fact that it's equal to ln 8, let me just separate this into a product. So it's going to be e to the power of 3t times e to the power of c. Now e to the power of c is equal to 8. I don't even need to use ln, just straight away replace it with 8. Now for part B, we have to find to the nearest 100 the size of the population at time t equals 2. So the formula we are going to use is p equals 8 e to the power times e to the power 3t. So at time t equals to 2, population is 8 e to the power 3 times 2. So that gives me the value of 3,227 point something. So the nearest 100 is 3,200. So that's the answer to part B. Now for part C, we've got to find the value of t when the population reaches 100 times its starting value. So the starting value of population, that was equal to 8. So we're simply asking at what time the population is going to be 8 times 1,000, so 1,000 times 8. So 8,000. So let's sub 8,000 into the formula for the population, which is 8e to the power 3t, and solve this equation. So e to the power 3t is equal to 1,000. 3t is equal to ln 1,000. So t is a third ln 1,000. Which gives you 2.3 hours, which is 2 hours 18 minutes. Okay, what are the limitations? So this is the exponential model. Any microorganisms could not really increase in this exponential way for unlimited number of, for limited time, because of due to illness, lack of space, food. So the population cannot grow at such a fast rate due to space, food, maybe illness, restrictions. There you go. Okay, moving on to example 28. Here we have a tank. This water in a manufacturing plant is held in a large cylindrical tank of diameter 20 meters, so radius is going to be 10, the height h. So at the bottom of the tank, the water flows out through a tap at a rate proportional to the cube root of the volume. So this means that it's pouring out, so that gives you the rate of change of the volume of the water, so that's dV dt. It's pouring out, so put minus. Let's use some constant of proportionality. Since they are using little k here, I'm not going to use the same letter. I'll use big K, or maybe you could use C. And it's the cube root of volume, so cube root of volume. So that is what we know, what's given. So it says show that t minutes after the tap is opened, dH dt is equal to minus k cube root of h for some constant h. So since they mentioned volume of a cylinder is the area of the base, so its area of the circle is pi times radius squared. So this is going to be, radius is 110, so it's 100 pi. And that's times by h, so it's 100 pi h. So as soon as you've written a formula, differentiated, that's going to be 100 pi. So that's dV dH. We want to get to the expression for dH dt. So this is the rates of change. So we're going to use the chain rule. dH, the start, dt at the end. Here we need to use the other variables. So dV, we're going to use volume because that's what's given. So dV dt is given by some constant minus k cube root of v. So let's sub these parts into the this expression. So the chain rule, dH dV is this one flipped, so it's 1 over 100 pi. dV dt is minus some big K, and then v to the power of a third. Now volume, as we've written here, is equal to 100 pi over h, so volume to the power of a third, so cube root is going to be 100 pi h to the power of a third. So let's substitute this into the equation. So it's 100 pi to the power of a third times h to the power of a third. And you can see that there should be a minus here, that this over here, which is going to be, we bring it to the top, minus 1, so it's going to be 100 pi to the power of minus 2/3. There's a minus in front, h to the power of a third. So this is going to be their k, with k equal to 100 pi to the power of minus 2/3. This can be replaced with k minus k to the power of a third. So that's been shown as required. For part B, we are going to show that the general solution to the differential equation may be written in the following form. So when we solve it, we should be getting something like that. I'm not sure what the power is. I think it's 2/3. Yep, 2/3. Sorry. Okay, so here's our equation, differential equation. So part B, let's have a go at solving it. So dh dt is equal to minus kh to the power of 1/3. So h's and dh's want to be together on the left hand side. So if I divide by h to the power of 1/3, that will become h to the power of minus 1/3 on this side. And then you've got minus k dt on this side. Give it an integral symbol. And let's integrate it. So add 1 to the power, divide by that power, gives me h to the power of 2/3 over 2/3. And this one is minus kt plus some constant c. So h to the power of 2/3 is equal to minus 3 over 2 kt plus 3 over 2c. We are aiming to get h on its own, so we are going to undo the power of 2/3. Yeah, I misread that one. That did say 3 over 2. Don't have my glasses. So raise it to the power of 3 over 2. That will bring us back to h. You're going to get minus 3 over 2 kt plus 3 over 2c to the power of 3 over 2. So now if you compare this with this, we'll have p equal to 3 over 2c and q 3 over 2k, original k. Not that it matters, because in general it is some constant, which is p, minus another constant, lots of t in brackets to the power of 3 over 2. Again, as required. So part C, find the values of the constant p, given that the height of the water is 27 meters at time 0, and 10 minutes later, at time 10 minutes, the height is 8. So let's use this information. So initially it's 27, and initially means when t is equal to 0, so you get p to the power of 3 over 2. So p is equal to 27 to the power of 2/3. So that's going to be 9. And let's use the second piece of information. So times t equals 10, h is 8. So 8 is equal, now p is already 9. So that's 9 minus q times 10 to the power of 3 over 2. So 8 to the power of 2/3 is equal to 9 minus 10q. So 8 to the power of 2/3 is 4. So it's 9 minus 4 is equal to 10q, giving me q is equal to 1/2. So the final formula for h will look like this. So h is equal to p we found to be 9, q is minus 1/2, t to the power of 3 over 2. So finally, find the time in minutes when the water is at a depth of 1 meter. So for part D, when h is equal to 1 meter, what is time that this will happen at? So replace h with 1, 9 minus 1/2 of t to the power of 3 over 2. So it's 1 to the power of 2/3 is equal to 9 minus 1/2 of t. So 1/2 of t is equal to 8. So t is 16 minutes. So that takes us to the end of chapter 11. Okay. and therefore you've got exercise 11K and the mixed exercise.